Welcome back, students. Mr. Urby here again with another video on the laws of thermodynamics. In the previous video we discussed the 0th law and the first laws of thermodynamics. If you missed those, then you want to go back and check that out. This video is going to focus on the 2nd law and the 3rd law of thermodynamics. But before I get into those laws, I need to define something called entropy. A lot of introductory physics courses like to define entropy as a measurement of disorder, where in a closed system, disorder would represent there being many possibilities of something happening. On the other hand, something that is ordered would have fewer possibilities of different outcomes. This definition is good to just get an idea of what entropy is. But in reality, entropy has a definition that relates to statistics. And I'm not going to get too deep into that, but I'll just explain that entropy describes the number of configurations that are equally probable to exist in a certain closed system. So for example, if I have a balloon with some gas in it, entropy is going to be something that describes how many different configurations can the gas molecules occupy that space of the balloon. It can occupy space in this way, or maybe this way, or any other type of configuration. Entropy is going to describe how many different configurations are possible with that system. So the higher the entropy, the more different states that system can occupy. In other words, the more disordered that system can be. Okay, the reason I need to talk about entropy before I get into the 2nd and 3rd laws is because both those laws have to do with entropy. So now I'm going to get on to that. The 2nd law of thermodynamics states that entropy in a closed system can never decrease, and it is only constant whenever certain processes are reversible. But pretty much entropy can never decrease over time. It can only increase or stay constant. So over time, in a closed system, things can get more disordered because entropy increases. Or in other words, there can be more possible states as time goes on. Okay, the 2nd law also states that systems tend towards thermal equilibrium, which means that temperatures move from hot to cold until the temperature equalizes and then they become the same temperature. Okay, so here's my 2nd law written out. I'm going to review it one more time. It states that entropy can never decrease, only increase or stay constant if processes are reversible, and systems move towards thermal equilibrium, which means that temperature moves from hot to cold until they become the same temperature. We see this happen all the time whenever we melt ice in a cup of water. Here I've done a cup of water where the temperature of the water is hotter, so I put a little TH there for the water, and then the temperature of the ice cube is colder, so I put a TC. Because of the 2nd law, heat is going to move from the water into the ice cube until they become the same temperature, which causes that ice cube to melt. Here I drew an arrow with a Q, which represents heat, and it flows from the water to the ice cube. Okay, and it would keep on flowing into the ice cube until they reach thermal equilibrium. Okay, and then if you think about entropy while that's happening, the 2nd law also states that entropy never decreases, only increases, or stays constant if the processes are reversible. Of course, after that ice cube melts into the water, it's not going to suddenly reverse back into its ice form. So in this case, entropy is going to be increasing. There's no reversible process there, which makes sense because as the ice cube melts into the water, that whole system can occupy more different configurations of the molecules within it. The molecules from the ice cube are going to be able to spread out within the water, which makes more different combinations of arrangements for those molecules to occupy. Whereas before, all those molecules were trapped in that ice cube and there were less possible configurations of those molecules. So yeah, I just want to emphasize that it states that entropy can only increase or stay constant in ideal scenarios. A lot of the times it can stay constant whenever things are already in equilibrium. So then whenever things are already not exchanging heat anymore, then entropy can be constant. And then also systems move towards thermal equilibrium. So things will move from hot to cold. So heat energy will move from hot things to cold things until they stabilize. And in that process, that system can occupy different configurations, different arrangements of states. Okay, now I'm going to move on to the 3rd law, which also involves entropy. Okay, the 3rd law of thermodynamics states that the entropy of a system can approach being constant, also if the temperature of that system approaches absolute 0. In chemistry class, you might remember learning about the Kelvin scale, but if not, there's a 3rd temperature scale in addition to Fahrenheit and Celsius called Kelvin that we use in science. The reason we use this scale is so that we can define the lowest possible temperature as 0, and we call that absolute 0. Okay, so it's not physically possible for things to have temperature below absolute zero. Because at that temperature, or at temperature equals 0 degrees Kelvin, there is an absence of heat energy in that system. And whenever things don't have heat energy, they cannot move. So if a gas, for example, was at absolute zero, it would just be stuck in place. Okay, and of course, whenever things aren't moving around anymore, they can't occupy different states as time goes on. Okay, so here I wrote out my law. Entropy approaches being constant as temperature approaches absolute zero, T equals 0 Kelvin. Okay, in that balloon example, whenever I was defining entropy, if the gas in this balloon is at absolute zero temperature, they'll no longer be able to float around the balloon as they normally would, so they wouldn't be able to occupy different states, which means that the entropy is going to be closer to constant. Even in things that are very solid like crystals, crystals have a chemical composition that is very set in stone and things don't really move around within the crystal. However, even in crystals there's microscopic vibrations and things do like wiggle a little bit within the structure. But if that crystal was at absolute zero temperature, then the entropy would reflect that, and there would be fewer states, so entropy would be constant. Okay, I know entropy can be kind of a confusing concept. We describe it as disorder, but also has some mathematical and statistical definition. If it helps to rewatch this video or seek out other resources to understand entropy, then I encourage you to do that, or ask us questions, because it's not an easy concept to understand. But anyway, I hope this video helps you get the gist of it and helps you understand the second and third law of thermodynamics. Okay, hope to see you guys next time. Thank you.